Hello everyone. In this video, we are going to solve a Smith chart problem. So a 70 ohm lossless line is used at a frequency of 300 MHz terminated by a load of 140 plus J91 ohm. Find the reflection coefficient, voltage standing wave ratio using Smith chart. So they have given the frequency and also they have given the characteristics impedance has 70 ohm and also the load impedance has 140 plus J91 ohm. Now we have to find the reflection coefficient, voltage standing wave ratio using Smith chart. So the given data is your load impedance and as well as the characteristics impedance, right? So the characteristics impedance is 70. They have mentioned it as lossless line. That is your dissipationless line. In the dissipationless line, we can write Z0 as R0. The first step is we have to find the normalized load impedance. So we know the load impedance, that is 140 plus J90. In order to find the normalized load impedance, we have to divide the load impedance by characteristics impedance. So the normalized load impedance is given by ZR by Z0. So it is given by 140 plus J91 divided by 70. You will get 2 plus J 1.3. So the normalized load impedance is given by ZR is equal to 2 plus J 1.3. So this 2 represents RA, that is your resistance, and then this 1.3 represents your reactance XA. Therefore, we can write the load point is located at point A. So in the Smith chart, so here this is your resistance scale and this is your reactance scale. So here, so this is where RA is equal to 2, and then we have reactance as 1.3. So it is positive, it should lies above the real axis. So in the Smith chart, so here it is reactance is 1.2 and here it is 1.4 and this is 1.3. So you have to trace this circle, and when RA is equal to 2, it is meeting at this point. So we have to mark this point. So this is your normalized load impedance. So this is your second step, and third step is draw a circle with O at origin and radius equal to OA. This is called constant A circle. Now what we have to do is we will mark ZR, that is your normalized load impedance at this point. Now you have to take the radius from the origin. So the origin point is where RA is equal to 1 from the unit circle. So this is your origin. Using scale, draw the line to the normalized load impedance. With that radius, draw the constant S circle. You have to draw the constant S circle. That is step 3. Then coming to step 4, the constant S circle cuts the right hand side of the horizontal axis at B, where reading is 3. So when you draw the constant S circle, so you'll be taking from the origin, you'll be taking the radius to point A. Point A is nothing but your normalized load impedance. So with that radius, you will draw by keeping this origin as a center, you will draw a constant S circle. So where it cuts the right hand side, that value is called as the voltage standing wave ratio. So it will cut at where voltage standing wave ratio is equal to 3. So in the right hand side where your constant S circle cuts the horizontal axis, that point is said to be B and the reading is 3. So that is said to be your voltage standing wave ratio. So in the question they have asked you to find the voltage standing wave ratio. So we can find the voltage standing wave ratio by the constant S circle at the right hand side. And the step 6 is extend the line OA to the point C at periphery. The angle corresponding is the phase angle psi of the reflection coefficient. Now in order to find the phase angle, so we'll be having OA as the radius, right? So you have to extend the periphery. So you'll be getting the phase angle as, so we'll be having the phase angle of the reflection coefficient in this third circle, right? So if you extend the periphery, then you'll be getting a phase angle has 29 degree. So once you get the phase angle, you have to draw an arc with radius equal to OA on the line for reflection coefficient at the lower side of the chart. So this is the lower side of the chart. So with the radius of OA, you have to draw the line. You have to draw an arc here. So if you draw an arc, this arc cuts horizontal line at D. So you'll where it's cutting, that is considered to be the magnitude of the reflection coefficient. Now we can find the magnitude of the reflection coefficient as well as the phase of the reflection coefficient. That is nothing but your reflection coefficient. So we have determined the reflection coefficient as well as, so this is the Smith chart. Okay, so we have plotted ZL, that is 2 plus J 1.3 here. So this is where your R is 2 and then your resistance is 1.3. Now this is your O, this is your origin. From O, by keeping O as origin, you have to draw a line. So this is considered to be the point A. With this radius, you have to draw the constant S circle. This is constant S circle. So once you have drawn the constant S circle, what you have to do is you have to extend this line to the periphery. So where it is cutting means it is cutting at 29 degree. That is your phase angle. So we can find the phase angle by extending this line, and also the right hand side of this horizontal axis represents your voltage standing wave ratio. So here the point is 3. So we can determine the voltage standing wave ratio as well as the magnitude and phase of the reflection coefficient. So just take the radius OA and then mark an angle, that means place a compass here, just cut an arc. So this is nothing but your magnitude of the reflection coefficient. So we can determine the reflection coefficient as well as the voltage standing wave ratio using Smith chart.